And I want to make sure before we actually get into this lab that everybody actually is really clear about what we're doing and what we expect. And most people seem to have a good, I think only one person actually didn't get the core objective even down. So most people did get what is our objective for today's lab, for this kidney regulation of osmolarity lab.
For mine, I put, how does varying H2O, salt, and or caffeine intake affect the volume, sodium chloride concentration, and specific gravity of urine?
Yeah, so exactly. It's pretty, and like in your, like, so Grace did that well. Some people would write things a little more vague, like how does salt or water affect, volume and specific gravity. You want to be very clear, like how does like the ingestion or intake of water and or salt and or caffeine affect the volume as well as the sodium concentration as well as the specific gravity of your urine. So in writing the objective, simple and straight to the point, but make sure it's non-ambiguous about what exactly the salt of what salt you're eating, saltiness of your urine. For the hypotheses, I'd say the one thing that was very common were people talking about increased. Group 1 will have increased urine production, because of blah. To increase or decrease, you have to have someplace you're starting from, right? And we're not starting from, there's not a normative value that we are working with that we can increase or decrease from. So we don't want to use these, increased or decreased, because that doesn't make any sense given that we don't have a starting point. So instead, you want to make sure you just kind of compare between the groups. That's the only thing we can do. We can say, like, I think this group is going to have the largest volume of urine, or this group and that group will both have very large amounts, or this group will have the least volume, and this group will be somewhere in between this group and that group. So you want to kind of be relative values in your predictions. Like, how is group 3 going to be different? Group 3, where they barely drank any water, is going to have, probably the smallest amount of volume output, because then you need the why. Not everybody did the whys all the time. Why would we expect there to be a very low volume of urine if you only drank a tiny little bit of water and ate salt tablets?
Because your body is going to hold on to the water
And why?
to maintain H2O balance and homeostasis.
Yeah, so that I want people to go that extra mile. Like, you're not going to pee out a lot because you need to hold on to that water and keep it in your body to maintain your water balance. So I think sometimes people are thinking it in their head, but you need to be explicit in the words as well. Or, like, I'm peeing a lot when I've drank a lot, not just because well, that makes sense, but because, like, oh, I need to release more water after I've taken in all this extra water to maintain my fluid balance, my water homeostasis. Right? If I take in a bunch of extra water, I need to let go of that, or else I'm not going to be in balance anymore. So in your hypotheses, you want to, and for each group, there's group 1, 2, 3, and 4. And there are, in fact, one person actually did it as a grid, and I thought it was great. There's volume, there's specific gravity, there's sodium concentration. And they just, for each one, talked about what they expected and why. And it could, and when you're talking about the volume, you can mention the other ones. Like, I think this will be the largest, or this will be one of the largest volumes, or this will be similar to or a little less than this other group or something. So you can mention the other groups, but make sure for each group you have a prediction and a reason for each of the 3 variables. So there's actually kind of 12 different things to deal with in here. Because when we look at our data, that's what we're going to be looking at. We're going to look at each group and what happened to each of these variables in each of those groups. And some people got really close. Some people were pretty far off. I do want you to have thought about this more before. So I think what I want to do, this is one of these things for those of you who, I'm going to put you in random groups. I am hoping that each random group has a mix of people who are more lost and people who really have got it. And what I want you to do is talk amongst the people who understand it more. Talk with, they say it's not even they say, I know it's one of the best ways to really learn stuff or really figure something out is to have to like explain it to somebody else. And so it's actually a really useful thing. Even if you're thinking, well, I got mine looks pretty good, being able to like really spend time in helping someone else understand it, actually, I think really helps you get even deeper. So what I'm going to do, 1, 2, 3, 4, 5, 6, 7, 8. We're going to split into like 4 groups right now. And I want you to kind of make sure your objective, hypothesis, source of variability are done, resubmit them, and then we will gather back together in a half an hour, and then we'll actually kind of look at the data and try to see, what actually happens in this thing. I want people to think about the kidneys really from this kind of dynamic standpoint of adjusting your osmolarity, adjusting your fluid, your water levels, adjusting your electrolyte levels to kind of maintain homeostasis. Does anybody want to share? Like, what does somebody have for like group one? Group one that just drinks a whole bunch of water and nothing else, and then we just sit for the next 2 hours and watch what happens to their urine. What would we expect?
So for group 1, I think that they would have like the second or third highest volume, because they're taking in the 800 milliliters, and then group 4 is also taking in 800 milliliters, but they're also drinking caffeine. So I think that group 4 would be the highest volume. So I thought that group 1 would be the second or third.
So why third? Third behind who?
Well, I wasn't sure because group 2 is also taking in the 800 milliliters. So I wasn't sure which one. Well, actually, yeah, let's say group 1 would be second.
Okay, and do people concur or have other ideas? Assuming silence is complicit. What about sodium concentration? How about somebody else? Group one. What would you expect for like the sodium concentration of the urine?
It should be pretty low because our kidneys are working to retain sodium concentrations.
Yeah, so there's actually two things going on. One is if you're not taking in much salt, then it's going to make sense that your body's going to conserve salt. You're not going to be peeing it out. And that on top of the fact that you're also probably going to have a very large volume of urine because of the water balance part. Remember, concentration is solute per liter. So if we have very little salt that we're actually letting go of and a large volume of urine, like together, those are both telling us low concentration of salt. Um, what about um, what about specific gravity for that group? For group one.
It'll have a lower specific gravity than the other groups because without the salt intake, the body's going to try to hold on to the salt and it won't be excreted in the urine because of the density in the urine.
Right. I mean, it's kind of the same idea that we're thinking about with the sodium chloride concentration, right? Specific gravity is ultimately telling us how much dissolved stuff is there in the urine, versus how close is it just to being almost like water. So, in general, I think, if you'd expect the low sodium chloride concentration is very likely gonna just be going along with a low specific gravity as well, right? So but think when I think of specific gravity and sodium chloride concentration in this lab, you know, unless there's something weird going on, those are probably going to be moving together, right? Because specific gravity is giving you a sense of how much dissolved stuff is there in your urine. So if you've got higher concentration of salt in there, it's going to be a higher specific gravity. Lower concentration of sodium chloride is probably going to be a lower specific gravity, right? So what about group three? What do people predict?
Lowest volume of water
And then why is that?
or urine, sorry. Because you're only adding 80 milliliters, so your body's probably going to hold on to the water to maintain the balance.
Exactly, right? So this idea, again, water balance. If you don't take the water in, you got to hold on to it. So that means there's going to be less that you're letting go of, in your kidneys. You're going to have more ADH and aldosterone trying to pull the water back out of the tubule back into your body, and you'll have less volume that you're actually peeing out. And what about sodium chloride concentration for group three? How about somebody new? You can do spin the bottle thing. Bah. Leah Lay.
Yes.
So what?
So for group 3, I put the volume of urine will be much lower compared to group 1, 2, and 4, and then highest sodium concentration in specific gravity.
And then why? What is the reasoning behind your between the
The reason is that because they have the least amount of water intake with the sodium intake compared to the rest.
and like I said, in the reasoning though, I want kind of a more complete, you want to kind of finish that thought. Like if you're not taking in much water, you're gonna have to hold on to the water in the body and not let it go to preserve the balance. Or if you've got extra salt coming in, you're probably gonna let go of more salt in order to maintain balance. So make sure in your reasons, like you really kind of are complete. Don't like have like don't have things that you have to kind of guess about, or I think I know what they're saying. And again, kind of the other thing to think about, if you have a very low volume, that means it's going to probably be a higher concentration. If you had the same amount of salt in a bunch of urine versus a little bit of urine, even if you had the exact same amount of salt, you'd still have much higher concentration in the small volume because the ratio of solute per volume is going to be higher. So, I mean, that's actually an important point we're going to be looking at when we look at the data. We'll look at sodium chloride concentration, which is that ratio of salt per liter. But we're also going to look at just how much actual salt got peed out, which we can calculate. If we know the volume and if we know like grams per liter of salt and how many liters of urine, then we can calculate how many actual grams did they pee out. And one of the things that we'll see is if you have a very limited amount of urine you're peeing out, that gives you kind of less, vehicle or whatever, less stuff to actually dissolve stuff in to get it out of your body. Right? So that's another thing. If you're not peeing a lot, one thing is means you're holding onto the water, you're probably dehydrated, but it also means you've kind of limiting your ability to actually get rid of stuff, because unless you have a reasonable volume of urine you're peeing out, you don't have the actual water to dissolve the stuff in to get it out of your body in the first place. Right? Like so, and it's part of the reason why even if your body is really trying to hold on to water, you're probably still going to have some minimal volume of urine you're creating, because you need to have at least some urine to at least dissolve stuff in to get it out of your body to pee it out. So yeah, when we look at the data, we'll look at the concentration, but we'll also look at like how much actual salt did they get rid of. So I'm taking a look here at. All right, so most people, there's still a few people who have not resubmitted their revised hypotheses. In the interest of making sure we get through everything, I'm going to keep talking. But before this like morning after early afternoon is done, if you are one of the people who has not resubmitted your revised hypothesis yet, please do that. Because it also means that you're going to be on track for the next part, which is analyzing and discussing, right? Because unless you have that first part solid, all the rest of it is going to be compromised.
Could we go over the sources of variability?
Oh yeah, no, thank you for that. Yeah, no, so that's actually important. What are some things people came up with there? Sources of variability for our experiment.
Age.
Age. I mean, maybe. I mean, that's one's not as clear for me. Although, I mean, in some ways you could say like older people are more likely, like especially older men are more likely to have like, what they call benign prostatic hyperplasia, where kind of impinges flow through the ureter, makes it harder to pee. So there could be impaired flow due to enlarged prostate in older guys, for instance. That could be related.
Could it be an issue of what people's like overall diets are? Like if they tend to drink like a lot of caffeine all the time, maybe it wouldn't be as dramatic during the
Right. In terms of caffeine, for
experiment.
being more habituated to the drug, the same amount of a drug. In fact, we see it in the lab. It's actually pretty hilarious when we do it in real life. The people who take the little caffeine tablets who are not used to drinking coffee, you just see them bouncing. They're fun to watch. They're usually having more fun than the people who are used to caffeine, who are just like, okay, I'm a little more awake, versus like, whoa, this is cool. Yeah, so for the caffeine particularly, having like more just tolerance to it will make a difference.
I also said how hydrated or dehydrated the subjects are before they come into the lab for the experiment.
Yeah, absolutely. So we do, in part of the process, we actually have them kind of void their bladder and start from scratch, or as a baseline after they take their water. But if they're already super dehydrated and they drink that water, it's probably what they should have been doing like before they started the lab. Like, it's not that common, but every once in a while I can see students who really should be better about hydrating themselves, where they'll drink like this huge thing of water and then not pee for the next 2 hours. It's like, all right, Dad, you need to drink more in everyday life here, right? So basically where their body is at the moment, when you're starting this, is obviously going to make a difference on how much you let go or hold on to, because it's not just what you're eating as we start the experiment, but it's also going to be how much salt and water you have, like from the first part of the day, that your body is still trying to balance out. So that's a huge one.
I was thinking height and gender and maybe BMI because it influences overall blood volume.
I mean, that could to some degree, although I think in terms of assuming you're at some particular, like kind of in your target zone, then the response to kind of stay in that target zone is probably going to be similar. Obviously someone who's bigger has more blood than someone who's smaller overall. But if either of those people then perturb that volume by like a liter, they both have to make kind of the same adjustments to come back to their target value. But yeah, taller people definitely, cardiovascular, I don't know if we talked about it, their heart has to work quite a bit harder. Like if you're like, really tall, that's a lot more gravity you've got to overcome to actually get the blood up to your brain constantly and not like pass out. Yeah, no, being shorter, actually, there's a lot less stress on your heart. So that's a real thing.
Would health conditions be one? Maybe the person's diabetic or they're pregnant?
Yeah, no, so that absolutely, like, and I mentioned even there's that other type of diabetes insipidus, where your kidneys are not conserving water properly and you just pee out much more than you should. You have trouble staying hydrated. Or if they're on one of these meds, people take diuretics for high blood pressure, they take it for edema or congestive heart failure, all sorts of conditions where people are just taking diuretics as part of their, the meds they're using to kind of stay healthy. So if they're on anything like that, that can make a big difference. Yeah, so there's lots of things that, which is part of the reason we're going to have a lot of data points and take a look and see what happens. Other thing I'll mention before we actually get into like the little video, specific gravity, when we looked at it in the urinalysis lab, it was just the color of a square on the multi-sticks. But there is another way to measure it that's kind of more the old school, and also kind of gives you more of, I think, a real sense of what specific gravity really is, the density of the pee. And I don't know, does anybody here ever brew wine or beer or anything? Anybody?
I made kombucha once.
Kombucha, you're probably not going to care as much about the alcohol content. You get some alcohol in there, but that's not the main reason. Like if you're making beer or wine, you actually are really, it's all about converting the sugar into alcohol. And you want to have a sense of how far has that gone? Am I done? Is it time to bottle or this or that? Sugar water is denser than alcohol. Alcohol is less dense. Sugar water is more dense. So you use a thing called a hydrometer. If you have let's say this is sugary. Let's say this is grape juice. And this is after the yeast has worked. Now this is wine. I should probably, let me give it a color. So here is my sugary grape juice. And here is my wine, which most of the sugars have been converted into alcohol. And from just looking at it, it's kind of hard to tell. But if you take it's called a hydrometer, this kind of weight, and you drop it in there. Whoops, I want to. There we go. This has a certain weight on it, and it is weighted so it floats. Doesn't touch the bottom, but it's part of it's out, part of it's down, and it floats at a certain level. And that's going to depend on the density of this. If I have alcohol here, this is like ethanol. This same weight, if you put it in there, it's going to sink way lower. Because this less dense stuff won't support it as much, so it sinks lower. More dense, it makes it float up higher. Right? That probably makes sense. It's kind of, if you've ever, I don't know if anybody's ever tried to swim in the Dead Sea in Israel, it's really kind of trippy. You just float around. You can't sink. You just lie there and you float. It's so salty that you just float. Or if if you're in fresh water versus salt water versus super salty water, you can even just feel it in how much your body floats as well, based on the density of the water you're floating in. So for getting specific gravity, we have the same same thing. We put the urine in a little vial, put the urine in there. We put this little float. The float in this case is going to be the urinometer. And you can just measure it. You can read on this little thing here, it'll say like 1.020 or whatever. It'll tell you the actual specific gravity based on how high or low the little float is floating in the urine. The one thing about taking it this way is you need enough urine to actually float it. So if, like in group 3, it might be that you are peeing so little that there's not much pee left at all. and you try to put the float in, I want to see where the float floats, but it's like, it's not enough P to make it float. So what that means is you cannot get a measurement. So the reason I'm saying that is, what would be the specific gravity in this case if I like try to get the measurement, but there's not even enough urine to float it? A little bit of a tricky question. Sometimes what people do is in their chart of like, what is the specific gravity for my reading here? They say, oh, 0, and that is not correct. 0 would mean like your P is like the density of a vacuum or something. That doesn't mean anything. What we would say is like null. There is no value. I think just making it clear, 0 is very different from there is no value, the null set. 0 would mean I measured the value and it's 0. It's like, how much juice is, or how much milk is left in the milk carton? 0 mils. That means that the milk is empty. There's nothing in there. This means I couldn't check. I couldn't get a value. I don't know. There's no value. 0 means I measured the value and the value was 0. So just kind of making that clear, that's kind of a good thing to always kind of remember, that 0 and no value are very different things, because 0 is a number. It's kind of like one of the big advances in mathematics, like kind of in Arabic scholars, after like, in Roman numerals, there is no 0. There's no way to represent 0 mathematically. It's like 1 and 2. But having a 0 totally blows mathematics wide open. But again, 0 is not a null. So like in the data, there's going to be some places where there's just no value for the specific gravity. And that means there wasn't enough urine to actually get a value. So blah, blah, blah. Okie dokie. So let's take a look then. All right, so I'm going to just show you, this is basically so you have a sense of how you would have actually got the data. So again, it's always, I think, good to get a more realistic sense. Normally it's kind of fun. Everybody's takes their little tablets and every half hour goes to the bathroom, and at first everybody's kind of shy and like puts paper towels around their beaker, so well, nobody will see my pee, and eventually it's like whatever, and sloshing around with it. All right, so I've been in group 3, which was just drinking 80 mils of water and taking 1.5 grams of salt, and this is a half hour after, since I did my initial voiding of my bladder and taking my treatment. And here's the amount of urine that I've got. Again, I'm collecting it every last drop, because I care about the volume. So this is not a clean catch like you were doing in the urinalysis lab. You're going to collect from the beginning to the end of the flow. And first thing I want to do is figure out the volume. And I can look here, roughly, it's less than 100. So when I think about which one of the cylinders makes sense, I'm going to probably take the one that's 100. This is going to get lost if I put it in one of these bigger ones here. So I'm going to pour it in. And I can go, and I can see it's about 31, 2, 3, 4, 5, 36 mils. And it's, don't worry about these values. You don't need to measure these values. This is just kind of showing how all these numbers in the spreadsheet that you're going to get were acquired. But again, so for every time, every half hour, each person in each group is going to measure 3 things. One is the volume. That is the first part. I'm also going to want to measure its specific gravity. For the specific gravity, I'm going to use this urinometer. It's basically a little vial and this float. It's kind of a hydrometer, like if you were making beer. It's the same idea. And depending on the density of the urine, this little float will float further up or sink further down, and the level of the urine on this little scale here is going to tell us the specific gravity. So typically you add about maybe 2/3 of the height here of the tube. You know, if you did not pee at all, you're not going to be able to get a value. And again, if you didn't get enough urine to actually float the float, you would just have no reading for specific gravity. You know, it wouldn't be 0. 0 is not valid. It would just be null. You don't have a value. But I have enough urine. I'm going to now put my float in, make sure it's not going to overflow. It looks good. I want to give it a little spin. I'm going to put it down here. Just kind of little style. You give it a little spin as you drop it so it doesn't stick to the walls. And then as it settles in, I can look here and it's about so about 0.028 is my, or 1.028 is my specific gravity for this. I'm gonna mark that down. Then the last part of this is I'm gonna get the sodium chloride content of my urine. For that, I am going to need a little test tube and a dropper right here. And so basically I'm gonna need 10 drops of my urine. And it matters that the drops are actual, like, well calibrated drops. This is a quantitative test, and it depends on numbers of drops that you're adding of different reagents. So it matters that I'm careful to add exactly 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 drops of my urine. Then I'm going to add exactly 1 drop of this potassium chromate solution. And now I'm going to add silver nitrate solution drop by drop by drop. And this forms a precipitate. And you'll see as a drop hits into the solution, it's going to turn brown for a moment, but then will probably become yellow again. And I'll keep adding drops of silver nitrate until this solution here stays brown. And the total number of drops that I add here are going to be the value of the total milliliters per, or milligrams per milliliter of sodium chloride that I have in there. And again, you can see it's yellow when I start. Does this help?
Yes.
Okay, I'm going to add in a drop. You see little brown show up? And then 2, 3, 4, 5, 6. I need to kind of look at it. Still looking 7, 8. Oh, it's not staying brown. 9, 10. Not quite yet. 11, 12. Ooh, it's almost there. 13. Probably give it one more. 14. That's brown. So 14. It took 14 drops. So that would mean I've got about 14 grams of sodium chloride per liter, or 14 milligrams of sodium chloride per liter in my urine, which probably makes sense given that I'm probably pretty dehydrated being in group 3. So, right, so that is basically the method. You know, everybody, some people in group 1, in fact, maybe I should show you just what that looks like, and then we'll look at the data itself.
We're going to be covering the kidney regulation of 1 is 2 liters. The 1 to drink that as quickly as they can.
Right, so this big glass here, this was the 0.8 liters, just so you get a sense. This little one is the 80 milliliters. And basically at time equals 0, they try to get it all down as much as they can. And again, some people are taking the salt tablets, and those, you want to take those, let them, you don't chew them or anything, because if all of a sudden you just had a lot of salt in your stomach that was just like all in solution right away, what would happen if the inside of your stomach was just super, super salty all at once?
Your body will want to get rid of it.
Think about more in terms of the physics of things. If you have, your stomach is kind of like a, this bag, and let's say you've got this super salty solution inside your body now in that bag, what's going to happen?
Would it suck the water out of the cells and the surrounding tissues?
It's going to suck water. Water's going to totally rush in, right? I mean, your whole body, you're like mainly water. You're going to have all this water rushing in. Your stomach is going to completely distend. And before you know it, you're going to be projectile vomiting. That's why you can't like drink ocean water to stay hydrated. The moment you got the ocean water down in your stomach, it sucks water in, and then all of a sudden stretches out your stomach and you're barfing it all out. So when we do these salt tablets, they dissolve slowly. So they, a little salt dissolves, you can absorb it, some more salt dissolves, and you can absorb it. But if you put all the salt in at once, you're going to have this super hypertonic solution that sucks in all the water and stretches out your stomach. And I can say when we were, it was like 20 something years ago when I was originally trying to get this protocol going, it's unpleasant to have projectile vomiting. So anyway, and for the caffeine, they're just no-dos. They're little viverins that are,
And 1 caffeine tablet, which is 200 milligrams of caffeine. Plugging Vibrant.
All right, so I have to show that so we get our. I'm just joking. They don't pay us for this. So then let's look at the data. Let's look at what comes out of it. Where is it? Oh, it's over on my other screen here. All right. All right, so on this chart, for each group, there's group 1, group 2, there's group 3 data, and there's group 4 data. The time equals 0, we don't actually record the data because we don't care. This is before they have actually done any of the stuff that they've taken into their body. This is before their body has had to respond. This is when you're doing the initial voiding of your bladder. We use this time to actually have people usually practice taking the measurements, using that method for measuring sodium chloride and things. So we don't care about time equals 0. What we really care about, this is when they took their treatment, when they drank their water or ate their salt or their caffeine. And now 30 minutes later, 60 minutes later, 90 minutes later, 120 minutes later, what are the values of the volume, the salt, and the specific gravity? Particularly here in group 3, you can see there are quite a few things where you can't measure specific gravity because there's not enough urine to float. Sometimes if they don't pee at all, you can't even measure sodium chloride concentration because there's no urine to do the little test with those, the potassium chromate and all that. So what we're going to do now is look at each of the each of the dependent variables and look at them between groups. And again, we can have somebody, what are we going to expect? If we're just looking at volume, what do you expect the volume's going to look like between group 1, 2, 3, and 4?
Group 4 is kind of the highest, then group 1, then group 2, then group 3.
Yeah, so let's take a look. We get something like this. Oh, and hold on, I need a... Yes, oh, wait, that's, and it's volumes. So here we see definitely group 3. If you look at the volume over time, group 3 is just obviously way less volume. Groups 1, 2, and 4 all had 800 mils of water they took in, all had appreciable amounts of pee that they were peeing out, which is kind of what you'd expect. If we compare the pure water to the caffeine group, they're pretty similar. You could say it looks like the caffeine group maybe peed out a little more than the pure water group, but it's not. This is one of these things. Does this seem like evidence that caffeine is a strong diuretic?
No.
Not really.
Not really. And in fact, if you look this kind of stuff up, there's a lot of evidence caffeine is really good at increasing intrarectal pressure, making you want to poop. That one is very clear. But this whole thing, there's this thing about, caffeine, you're gonna dehydrate drinking coffee because you're gonna pee out more than you get in. It's like, that's kind of silly. You maybe pee a little more, but more you're peeing out more because you're just drinking a lot of water. There is some evidence that it can be a slight diuretic, but it definitely, I've done this one for a long time. There can be a little bit of increase, but it doesn't even just seem to be, we'll talk more about it. It seems to be about getting rid of more salt and then the water following the salt. Group 2, we didn't talk about that as much. Does this make sense that group 2 has kind of a bit less water leaving than group 1 or 4?
Yes.
And why is that?
Is it because you're putting in extra salt, so your body's going to hold on to the water to kind of maintain that balance?
Yeah, so that's where you have the water, but also salt. So you're not going to want to release the water as fast because you need to, keep it in to keep, to deal with the fact that you're saltier inside as well. So you're going to have to be releasing salt and water, but it's not going to be as dramatic as all we need to do is get water out of our body. You need to be a little more measured about it because you've increased the amount of salt in your body as well now. So this is all pretty nice. If we look at sodium chloride concentration, this one, if you look group 3, like, oh my God, they had way higher concentrations of salt in their urine compared to all the other groups. And everybody else, and if you look, group 2 had a little elevated, which is kind of what we'd expect. You took in more salt, you'd expect to pee out a little more. Although to really know, and I should mention that 1.5 grams of salt that people eat is not a crazy amount. It's like kind of like a big bag of pretzels. We used to do this with more salt, but people would get very uncomfortable. So trying to do it so people did not feel so bad. Figured it was better to err on the side of not as dramatic results, but not have people feeling crappy. If we look at specific gravity basically mirrors the salt concentration, which is what we'd expect, right? Salt concentration, specific gravity are both kind of measures of dissolved stuff in the urine. The last thing I'll leave you with that I think is interesting is sodium chloride amount. So this is basically the multiplication of the volume times the sodium chloride concentration. So this would be if you just evaporated the pee that was in the collection, how much salt is left? Weigh how many grams of salt was actually in that urine you peed out. And if you take a look, group 3 actually had the least amount of salt you actually got rid of from the body, even though they had the highest concentration. Why? How can it be that they had such a high concentration, but they actually peed out the least amount of salt?
Was it like you were saying where it's not the vehicle for the salt to leave their body?
Exactly. They packed in as much salt as they could in the urine they had, but they had such small volumes. This is as much as they could get out. It was part of the reason why you don't want to be dehydrated for lots of reasons, but one is that volume of urine is part of the way your body helps get rid of stuff to maintain balances or get rid of wastes. And if we take a look, group 2 compared to group 1, we see that group 2, which took the extra salt tablets, actually did ultimately get rid of more salt from their body, which is that's nice. And then group 4, the caffeine group, this is something that is pretty reliably, I've done this thing for 20 years. Caffeine does seem to cause more salt to leave the body than just drinking pure water. And I think that probably also is related to the caffeine causing, a little more water to leave the body as well. If you're not holding on to as much salt, you're probably not holding on to as much water because the water follows the salt. But basically what you're going to do for your write-up is take this data. Now you have the sodium chloride concentration as well as the salt amount, the volumes and the specific gravity, and you can compare them to your hypotheses and talk about if this supports your hypotheses, what it all means. So not as much fun, but not as stinky. I never quite realized, because we talked about smell adapting very quickly. Like I would not, if you're in the lab with everybody with beakers full of pee, and you don't realize that it actually smells totally like pee in there until you've been out of the room, and then you walk in after, and then it's like, whoa, this place smells like pee. So any questions about this? No. Yeah, I mean, the main write-up isn't due for a while, but your pre-lab is, please, if you have not scanned and turned in your revised pre-lab, please do that this, once we're done with the Zoom right now, which we are.